Hello everyone. Hope you are doing very well. So today, as you all know, that we are going to cover the part 7 of theory of our chapter coordination compounds. So let's begin today's topic, that is NCERT chapter 5 coordination compounds theory part 7, and today we are going to see the NCERT section 5.5.4 to 5.5.5. This is disclaimer. The objective of today's lecture, so today, after attending this lecture, you will be able to understand the nature of bonding in the coordination compounds in the crystal field theory. Okay, so after attending this lecture, you will be able to understand the nature of bonding in the coordination compounds in terms of crystal field theory. The topics that we are going to cover today, according to the NCERT, they are like, first is the section 5.5.4 crystal field theory, CFT. So in this, there are two sections. The first is CFT of octahedral complexes, and another thing is the crystal field theory or CFT of tetrahedral complexes. So this octahedral part we have covered in the previous lecture. Today we are going to see the crystal field theory of tetrahedral complexes, and then we also cover the part of the section 5.5.5, the color in coordination compounds. So let's begin. So the assumptions of the crystal field theory in the tetrahedral complexes. So we are going to cover the tetrahedral complexes part under the crystal field theory today. So what are the assumptions that we had we have to made while studying the crystal field theory in the tetrahedral complexes? The first is the degenerate d orbitals. In an isolated gaseous metal ion, the 5 d orbitals, which are dxy, dxz, dyz, dx square minus y square, and dz square, these are the 5 d orbitals. They are degenerate. Degenerate means they all have same energy. Okay, this is the first assumption we are considering. You can see this figure 5.9, showing the d orbital splitting in a tetrahedral crystal field, right? So we are having this 5d orbitals, dxy, dxz, dyz, dx square minus y square, and dz square in a degenerate form here in the free ion, in the isolated gaseous metal ion, and these 5d orbitals are degenerate, having same energy. Okay, and after after the increasing of the energy, they get still the same energy. That means they are still degenerate, and they get average energy of d orbitals in the spherical crystal field. And then after which, when you increase more energy of it, they will split into the two categories, or in the two groups, the T2 and the E groups. Okay, so we will talk about this later in this lecture. Until now, we are considering our first assumption, that the degenerate d orbitals, that in the gaseous metal ion we have 5 d orbitals, named are given like this, and they are degenerate. That means they are all these 5 d orbitals are having equal or same energy, similar energy. Second assumption is the approach of ligands in a spherical field. So how in a spherical field the ligands are going to approach towards the central metal ion? So the ligand approach is, ligands move closer to the metal ion, central metal ion, right? So there is central metal ion present already, okay, having 5 d orbitals, which are degenerate. This is the first assumption we have made. Second assumption is, now we have to make the bond, like the central metal is have to make the bond with the ligand. So ligand is going to approach towards the central metal ion to form the bond. So the ligand move close to the central metal ion. That's what we are saying, that ligand is approaching towards the central metal ion. Okay, so ligands is approaching towards the central metal ion. hypothetical spherical field. So hypothetical spherical field means that around the central metal ion, this ligand approach and the 5d orbitals which are degenerate, these are going to create a uniform spherically symmetrical electrostatic field around the central metal ion. Okay, so this is a hypothetical spherical field which is symmetrical also, and it is electrostatic in nature, and it is uniform, which creates around the central metal ion. D orbital energy increase. So what happens? The repulsion is going to be observed between the d electrons in the metal and the ligand electrons, which is ligand like approaching towards the central metal ion. This is going to cause the raise in the energy of the 5d orbitals. Okay, so what we are saying that so we are basically considering our second like assumption, in which we are studying the approach of ligands, how the ligands is going to approach in a spherical field around the central metal ion. Okay, so ligands is going to move closer to the central metal ion, and it is going to enter into the hypothetical spherical symmetrical electrostatic field which is creating around the central metal ion, which is present around the central metal ion. Now what does happen by that? The ligand is already approaching toward the central metal ion, and it is carrying negative charge, right? It is carrying electrons with it, and also in the metal d orbital it is also having d electrons, right? So the d electrons the d electrons in the metal and the electrons of the ligand are going to face the repulsion between them, and due to this repulsion between the d electron and the ligand electron, the energy of the all 5 d orbitals of the metal will going to be increase. So you can see that in this diagram we are having these 5 d orbitals. They are degenerate, they are having equal energy, and they are having lower energy. But when the ligand is approaching towards the central metal ion and entering into its spherical symmetrical electrostatic field which is present around the central metal ion, then the repulsion between the d electrons and the ligand electrons happen, due to which these all the 5d orbitals energy is increased by some amount. So they all become they will go from here to here after the raise in the energy. Okay, but in between them, in between the 5d orbital, their energy are same, but comparatively from the previous state of the all 5d orbitals, their energy is increased, okay, due to the repulsion between electron and electron from the ligand and the electrons. And they will, like, all the 5d orbitals will come here in the diagram. You can see this is the phase which is showing the approach of ligands in the spherical field. Okay, degeneracy maintained. Now all the 5d orbitals remain at the same energy level. As I said that they raise their energy. Okay, all 5d orbital raise their energy from the previous like in the degenerate form, when there was no ligands, only metal ion is there, then all the 5d orbitals having lower energy. But when the ligand is approaching towards its spherical field, when ligand is moving closer and closer to the central metal ion and entering to its symmetrical spherical electrostatic field, then the repulsion happens, or the, you can say, electron electron repulsion happen between the d orbitals and the ligand, due to which the energy raised of all the 5d orbitals, but they are still having, like, all the d orbitals still having or still remaining at the same energy level, right? So that means the degeneracy is maintained among them. Now barycenter, if we talk about, we have also talked about the barycenter in the octahedral complexes when we studied the crystal field theory in the octahedral complexes. So barycenter, so this elevated still degenerate energy level is called the barycenter. Okay, so now all the 5d orbitals from the previous state raise their energy to some amount, and this elevated still degenerate. This is an elevated energy, but still this is degenerate. Okay, energy increased all the 5d orbital, but among them the energy level, they are still remaining at the same energy level, so they are still degenerate. Okay, so energy level, this energy level create is called the barycenter. Okay, So what we are calling the barycenter as this pink or this dotted line representation, this blue color dotted line representation, this is representing the barycenter of this elevated, but still this is a degenerate energy level. Okay, so this is a barycenter in this diagram, if you can see. Okay, third assumption we are going to make is splitting in a tetrahedral field. So how splitting is going to be in the tetrahedral field? So tetrahedral geometry, the first of all, the thing is we are talking about the tetrahedral field. That means the geometry of our complex is going to be tetrahedral. We have talked about the octahedral, in which the geometry of the complex was octahedral. Here the geometry of the complex will be tetrahedral. Tetrahedral means the 4 ligands. Tetra means 4. Okay, so here in this case, with the central metal ion, only four donor atoms can bound, or you can say only 4 ligands can arrange themselves around the central metal ion in a geometry. Okay, so how the tetrahedral geometry is going to make for the complex? The 4 ligands are going to place at alternate cube corners around the metal ion. Okay, cube corners, if you consider a cube, okay, cube is basically a 3D form of square having all the sides equal, right? So when you take the square in the 3D form, that forms a cube, and we are saying that alternate cube corners, okay, alternate cube corners are going to occupy by the 4 ligands around the metal ion, and consider metal ion is at the center of that cube. Okay, inverted splitting. Now, why we are saying inverting splitting? So leads to a d orbital splitting pattern inverted from the octahedral complexes in the 2 sets as E and T2. Now here what is happening? Why we are calling inverted splitting? Because as compared to the octahedral complexes, here the splitting is inverted in the inverted pattern. Okay, so the d orbital splitting pattern is inverted from the octahedral complexes, and here again the splitting is into the 2 sets. First is E and the another is T2. You observe that we are not using the G subscript here, E, G and T2 G, which we have done in the octahedral complexes, right? Why? We will talk about this. First, let's cover the E set, which includes the 2 orbitals of the of the 5 d orbitals. So the 2 orbitals are dx square minus y square and dz square. So these are the 2 d orbitals that comes under the E set. Here, the metal lobes lie along the Cartesian axis. Okay, Cartesian axis we are considering x, y and z axis in the 3D plane. So metal lobes, that means the metal d orbitals. The metal d orbital lobes lie along the Cartesian axis in the E set of the tetrahedral complexes in the tetrahedral field. So ligands here, when they move closer to the central metal ion, so their ligands are going to position themselves in those Cartesian plane, okay, to form the bonding or strong bonding with the metal. So how ligands are going to place themselves? The ligands are positions between these axes, the Cartesian axis, the x, y and z axis. So along the axis is the metal d orbital lobes, and in between the axis there are ligands positions. Okay, so if you remember, in the octahedral complex, in the E set for the dx square minus y square and dz square, the ligands and metals were both lying along same axis. Remember? But here what is the case? The pattern is inverted, that the metal lobes are still lying along the Cartesian axis, but the ligands are positioned between the axes. Okay. Now, due to this, the repulsion will be lesser. Comparatively, from the T2 set, comparatively, if you place ligand and the metal lobes along the same axis, then the comparative to that repulsion, Here, the metal orbs are along the Cartesian axis and ligands are positioned between those axes. So, repulsion will be comparatively lesser experienced by these orbitals. That means the energy is going to be lowered, right? So, energy is going to be lowered for the E set. Remember, in the octahedral complexes, the energy was higher in the E set. I said the reason due to the overlapping of the metal lobes and the ligands positions along the similar axis. Okay, but here in the tetrahedral field case, the E set energy is lower compared to the T2 set because they experience less repulsion because of the position of the ligand, which is between the axis, between the Cartesian axis and the metal lobe position, which is along the Cartesian axis. Now, if we define the T2 set contains 3d orbitals dxy, dxz and dyz. So here the metal lobes will point between the Cartesian axis. Okay, here what happens? The metal lobes is between the Cartesian axis. That means the metal d orbital lobes are present between the Cartesian axis and the ligands are pointed more directly towards these orbitals. Okay, so ligands are pointed more directly towards the orbitals and the metal lobes are between the Cartesian axis. Okay, that means the direction is going to be similar. Okay, the metal lobe direction between the Cartesian axis and the ligands direction, they are also going to directly towards these orbitals. That means these metal lobes orbitals. So direction of both ligands and the metal lobes, metal d orbital lobes, are going to be in the similar way or in the same axis, due to which here the T2 set orbitals will going to experience the greater repulsion due to the d orbital electrons and the ligand electrons, because they are pointing towards each other in a similar direction. Okay, due to which here comparatively from the E set the repulsion is more, and due to this more repulsion of electron on electron, energy is raised. Okay, so between the E set and T2 set, T2 set energy is higher, E set energy is lower. The reason is simple, that in the E set the metal lobes are along the axis and the ligands are present between the axis. Meanwhile, in the T2 set, the energy is higher because metal lobes are pointing between the Cartesian axis and ligands are also in a similar direction. Okay, due to which there will be greater repulsion, which cause the raise of energy. Let's see the crystal field theory in tetrahedral complexes. Rarely it show low spin. Okay, that means smaller energy preference, so it prefer the energy, so small delta t. Now here we are considering delta t. T means tetrahedral. T is representing the tetrahedral, that we are talking about the tetrahedral field, tetrahedral complexes. So delta t, that means crystal field splitting energy in the tetrahedral complexes is smaller, means the energy gain from placing the electrons in the lower energy orbital is often less than the energy required to pair them up, that is pairing energy. Okay, remember we have studied about the pairing energy, which is the energy which is we needed to require the electrons to pair up. Okay, so we are saying that if delta t is small, it does mean that energy which is we are gaining from placing the electrons in the lower energy orbital. Okay, lower energy means here lower energy orbital is E set. So if the electrons are placing in the lower energy orbital, and the energy we are gaining from this is going to be lesser than the energy, or you can say lesser than the pairing energy, which is we require to pair them up. Okay, that cause the delta t value smaller. Okay, so this is the energy preference in the tetrahedral complexes case. Dominant configuration, what does this mean? That energetically more favorable for electrons to occupy the separate orbital with parallel spin. So it is more energetically more favorable that electron occupy separate orbitals with the parallel spins. That means other than or you can say like it don't need to be pairing up. Okay, other than the pairing up, the electron should occupy separate orbitals with the parallel spin, and this is going to be energetically favorable condition. So this is going to be the dominant configuration, which is going to define the, or which is going to decide the configuration in the tetrahedral complexes case. Okay, and what is going to be the outcome? As a result, tetrahedral complex almost exclusively exhibit the high spin configuration. That's why we are saying that tetrahedral complexes almost exclusively exhibit high spin configuration. Okay, so due to these reasons, this is going to be the outcome, that tetrahedral complexes are exhibiting exclusively high spin configuration. So it rarely show low spin configuration due to the energy preference, which is going to be smaller delta T, because the electron should occupy the lower energy orbital, or electron should go into the uh, like uh, go into the separate orbitals with the parallel spin rather than pairing up. Okay, and this is going to define their configuration, which is going to be exclusively highly or high spin configurations. Okay, so they rarely show low spin. Now, as I said that no G subscript is here. So why no G subscript is present in the E or the T2? So symmetry requirement. What does that mean? That the G subscript signifies the presence of a center of symmetry in the complex. If you are placing a G in the subscript for any set of orbitals, that means you are signifying that there is a presence of center of symmetry in our complex, whether it is octahedral or tetrahedral. But here we don't use any G subscript because there is no center of symmetry in this complex. Okay, so complexes with G means, so octahedral and the square planar complexes are the complexes which possesses a center of symmetry. Okay, so in the octahedral and the square planar complex, they are having center of symmetry, due to which, you remember, they have this EG set and T2G set. Okay, G subscript was there. Tetrahedral geometry, there is no center of symmetry is going to be present in the tetrahedral geometry. That's why we are not placing any G subscript in the E or the T2 set. Nomenclature consequence. So due to the lack of the symmetry in the tetrahedral geometry, the G subscript is omitted from their d orbital energy level labels. Okay, so why? Because there is no center of symmetry, or no symmetry is going to be there. That's why the nomenclature is going to be like, from this, the nomenclature, we remove this G subscript from the d orbital energy level labels. So it is going to be E and T2G. It is going to be E and T2, not EG and T2G. So G will be removed due to the lack of the symmetry in the tetrahedral geometric complexes. Let's see the crystal field theory in the tetrahedral versus octahedral complexes. So inverted d orbital splitting. So if you compare between the tetrahedral and the octahedral complexes, if you see in the terms of crystal field theory, so first point is inverted d orbital splitting. So octahedral versus tetrahedral, if you see, in the octahedral complexes, the EG orbitals are higher in energy and T2G than T2G. Okay, so in the octahedral complexes, if you remember, EG is placed higher than the T2G. So EG orbitals are having higher energy than the T2G set. But in the tetrahedral complexes, this is reversed. The EG is having lower energy, E is having lower energy, T2 is having higher energy. So energy order will be, the T2 orbitals are higher in energy than the E orbital. This is going to be the energy order, that T2 orbitals are higher in the energy than the E orbitals. Now what is the reason? So T2 orbitals in a tetrahedral field experience more repulsion. We have studied about this, right? That T2 orbitals in the tetrahedral field will experience more repulsion due to the orientation, okay, of the metal lobes and the ligands. So from the ligands and then the e orbitals, leading to their high energy. So comparative to the e orbitals, T2 orbitals in the tetrahedral field experience more repulsion from the ligands. There will be more repulsion between the d electrons and the ligand electrons, due to which the energy is higher for T2, okay, in the tetrahedral complexes. Second thing you can second point you can take to compare between the tetrahedral and octahedral complexes in terms of CFT is the smaller splitting energy, that is delta T, is smaller in the tetrahedral complexes case. Magnitude, so what decide the magnitude? So delta T is significantly lesser than the delta O. Crystal field splitting energy of octahedral complexes is higher than the crystal field splitting energy in the tetrahedral complexes. You can see in this other way. Okay, so delta T is significantly lesser than the delta O. Quantitative relationship. So quantitatively means if you want to give a quantitative like mathematical term, or if a like measure through which you can measure something. So specifically the delta T is 4/9 of delta naught for the same metal ligands and metal ligand distances. Okay, this is going to be the case between the delta T and the delta naught, that delta T is 4/9 times of delta naught. Okay, so delta T is smaller than delta naught. Now what is the reason for smaller splitting? Why the splitting, crystal field splitting in the tetrahedral complexes is smaller? What is the reason behind this? So in the tetrahedral geometry, the ligands are more and do not directly point along the axis of any d orbitals as effectively as in the octahedral complexes. What we are saying? We are saying that in the tetrahedral geometry, comparatively, in the tetrahedral geometry, ligands that are not going to directly point along the axis of any d orbitals. Okay, their direction may be same, but along the similar axis or along the same axis, the ligands are not going to place themselves in the similar axis as the axis of the d orbitals. Okay, as effectively as in the octahedral complexes. In the octahedral complexes, this overlapping between the d orbital lobes and the ligands along the same axis is very, very much efficient. Okay, but here in the tetrahedral complex, this positioning of the ligands along the axis of any d orbital is not as effective. So this is going to lead to less pronounced orbital splitting, due to which the splitting will be lesser comparatively from the octahedral complexes. This is the reason behind the smaller value of delta T than the delta naught. Explanation of crystal field splitting of tetrahedral complex. So the CFSC diagram. Let's see the crystal field splitting energy diagram. So this is the d orbital splitting in a tetrahedral crystal field, which is we are seeing having we are having d orbitals free ion. They are degenerate. They are having same energy, and when the ligands are move close to the central metal ion and enters to its spherical symmetrical electrostatic field, the energy is raised of these 5d orbitals due to the repulsion of electron from the ligand and present in the metal d orbital. The electron repulsion will cause the raise in the energy, but still they are degenerate. They are having same energy, so they are representing the average energy of d orbitals in the spherical crystal field. Now when ligands are going to bond with a central metal ion, so again due to the raise and more energy or due to the lower energy, based on the placement of the or orientation of our geometry, that how the ligands are and the metal lobes are going to approach towards each other, how they are placed each other in the Cartesian plane, that are going to affect the energy of the 5d orbitals, according to which they are going to split it between the two sets T2 and E, where E is having the lower energy compared to the T2 set. T2 is containing dxy, dyz and dxz orbitals. E is containing dx square minus y square and dz square orbitals. Okay, so you can see this is representing the barycenter, and the energy difference between these two or splitted set is denoted by the crystal field splitting for the tetrahedral complexes delta T. And from this barycenter, the energy is raised to the T2 set by 2 by 5 delta T, and energy is lowered by minus 3 by 5 delta T to the E set. Okay, so this is showing the splitting of d orbitals in tetrahedral crystal field. And energy, you can say this arrow is representing the increase of energy. So energy difference, if you talk about like delta T or 10 dq, the definition is that energy difference between the E set, which is lower here in this case, lower energy, and the T2 set, that is higher energy. Okay, so energy difference between the E set and the T2 set is the energy difference, which is represented by delta T. Here in this diagram also you can see here this is present. It is named as tetrahedral crystal field splitting energy. Notation, you denote it by delta T. T represents the tetrahedral complex, or 10 dq. dq was the unit for the measurement of the energy in this complex. So this is the diagram we were explaining, and energy contributions, if you want to see what are the contributions of energy from the two sets. So each electron in the E set stabilize the complex by minus 0.6 or minus 3 by 5 delta T energy. Okay, so each electron which is going to be filled in the E set, okay, is going to stabilize the complex by this much amount of the energy, which is minus 0.6 or minus 3 by 5 of delta T. Okay, we are using stabilize because here the energy is lower for the electrons in which the complex will be stable. Each electron filling in the T2 set is going to destabilize the complex by positive 0.4 or 2 by 5 of delta T. This much amount of energy, each electron with this much amount of energy is going to destabilize the complex. Why we are using destabilize? Because this is a positive energy, higher energy of electrons. That means the complex will be destabilized. Okay. CFSE calculation for the tetrahedral compounds. Let's see. So CFSE is given by the formula minus 3 by 5 Ne plus 2 by 5 Nt2 multiplied by delta T. Okay, remember we have another term also like plus Mp in the octahedral crystal field splitting energy, right? Where where P is denoting the pairing energy and M is denoting the difference of paired electron set in the splitted d orbitals and the degenerate d orbital. Remember, that is absent here. Okay, here only the CFS is given by this much of formula, where this this N with the E is representing the number of electrons in the E orbital in the E set, and here Nt2, here N is representing the number of electrons which is going to be present in the T2 set. Okay, delta T is again the CFSE for the tetrahedral complexes. So here the N is denoting the number of electron for each sets, and delta T is representing the crystal field splitting for the tetrahedral complex. So this is the formula. You can use this for the calculation of CFSE for tetrahedral compounds. Let's see the example of the crystal field splitting energy calculation in the cobalt plus 2 complex, which is possessing a tetrahedral geometry. As you know that cobalt in the 2 plus is having this configuration argon 3d7. Argon have 18 electrons, stable configuration, and outermost configuration for the cobalt 2 positive will be 3d7. Now this figure here is representing the crystal field splitting energy splitting diagram of cobalt plus 2 complex. So from here from the average energy of d orbitals, this is going to be split into two parts, the T2 and the E. E is having the lower energy, T2 is having the higher energy. So what we have considered that first of all the electrons will be filled with the parallel spins rather than pairing up, right? So first you fill the electrons in the singly paired, first of all in the lower energy level. So in the E set you fill 1 2, and then in the T2 set you will fill 3 4 5, then still 2 are remain because D7 is there. So if D5 is completed, 2 is remains, so then 2 is going to be filled up again in this E set and after pairing up of the electrons. So this is the splitting representation for the cobalt plus 2 tetrahedral geometry having D7 configuration. So the configuration becomes E4 T2 3. In the T2 we have 3 electrons, in the E we have 4 electrons. If you want to calculate the crystal field splitting energy, then you can again use the formula, right, where minus 3 by 5 N-T2 plus 2 by 5 Ne delta T. Now you know the number of electrons in the E set is 4, right? That is going to be that is what you are going to place here in the formula with the at the place of N with the E. And the number of electrons in the T2 set is 3. 3 electrons are there in the T2 set, so you are going to place the 3 at the place of N with the T2. So the CFSE will become minus 3 by 5 times 3 plus 2 by 5 times 4 multiply by delta T. You can solve it and you will get the crystal field splitting energy calculation for the cobalt plus 2 complex is equals to minus 0.2 delta T. This is an example just to show that how to calculate the CFSE for a particular complex or metal complex having some oxidation number, right, after the splitting of their electrons in the E and the T2 set. Let's see a table for tetrahedral complexes with their crystal field splitting energy. Here in this table we have 3 columns: d electron count, electron configuration for high spin, and the CFSE for a high spin formula. Because it rarely show low spin in the tetrahedral complex, we rarely show the low spin. That's why we are only taking the case of high spin here. So if the d electron count is d1, the electronic configuration will be E1 T2 0. CFSE will be minus 0.6 delta T. Similarly for d2, E2 T2 0 will be the configuration and minus 1.2 delta T will be CFSE. Similarly, you can see we have for different d electron count we have different CFSE, and for d5 the configuration is E2 T2 3. That means E is having 2 electrons, T2 is having 3 electrons. The CFSE is 0. Okay. Similarly, the 0 CFSE is for D10 having the configuration E4 T2 6. The CFSE is 0. Only for these two it will be 0. Other than that, everyone is having some amount of CFSE formula. Right? If you observe the pattern, we have D1 CFSE and the D6 CFSE similar. Similarly, D2 CFSE and the D7 CFSE similar. D3 CFSE and the D8 CFSE similar. Similarly, D4 and the D9 CFSE is also similar, right? You can predict this by using the formula for the CFSE calculation, right? Okay. Let's move to our another section, 5.5.5, the color and coordination compounds. Distinctive property of transition metal complexes. So let's see. The one of most noticeable features of transition metal complexes is their wide range of colors they show in their compounds. and the origin of color. So how the color is going to be, like, what is the origin of color in these compounds? Color arises because the complex absorbs some wavelengths of visible light from the white light as it passes through the sample. Okay, so what happens when the light has when the white light pass through the sample, the complex is going to absorb some wavelength of visible light. Okay, and due to which color is going to be arise in the complex. The absorption, what does mean absorbed? So absorption means that the light that emerges from the sample is no longer white, right? So if you are having a, you remember prisms concept. So if you are having our complex, and white light is passing through it from the one side, the another side will not be the white light coming out from it. Okay, because some wavelength of visible light is already absorbed by the complex, so the light that is going to be emerged out from the sample or the complex is going to be of some other color, not the white color. So complementary colors, so basically color of the complex, the complex that are going to be the color one. Okay, so the color that is going to be denoted or that is going to be represented by that complex is complementary to the color of the light that is absorbed by it. Okay, what I'm saying, that if you pass the white light through the complex, it will absorb some wavelength of visible light. The light which is absorbed by the complex and that color of the light, so what you will see, what is the complementary color of that light, and that complementary color is going to be the final color of our complex. Complementary color is the color that is results from wavelength of light that are not absorbed, or that the light that is left over. Okay, that wavelength of light is going to be decide the complementary color. For example, if you have a complex which absorbs green light, it is going to exhibit the, or it is going to appear as red in color. It absorbs the green light, but it is appearing red in color. Okay, so the complementary color is the color that is going to be shown by the complex. Okay, complementary from the color of the light that is absorbed by the complex. Relationship between the absorbed and the observed color. Okay, absorbed means what the color of the light that it has absorbed. Observed means what is the color that it is showing. Okay, in which it is appearing. You can see this table having 4 columns in it. Coordination entity, the coordination complex we have given. Wavelength of the light it is absorbing in the nanometer. Then the color of light that is absorbed by the complex, and the color of coordination entity that is going to be shown by the complex. Okay, so if this is a complex of cobalt, the wavelength of light it is absorbing is 535 nanometer. The color of light that it absorbed is yellow color, but it is going to show the color as violet. So the complex will going to be violet in color. Similarly, these other complexes given. So the cobalt complex, 500 nanometer wavelength of light it has absorbed. The color of light it is absorbed is blue green, but it is going to appear in the red color. Then next complex having the wavelength of light absorbed is 475 nanometer. The color of the light it is absorbed is blue, but the color of the complex will going to be yellow orange, complementary to the blue color. Similarly, for this complex, the wavelength of light it is absorbed is 310. The color of light it is absorbing is ultraviolet. That means it is not going to be present in the visible range, in the visible region. Okay, but it is going to show the complementary of that ultraviolet light color that is going to be pale yellow. Similarly, the other two complex will also going to observe the particular wavelength of light and the color, but it is going to show the complementary color of the absorbed light. Explanation of color using the crystal field theory. How you can relate the color of the complex with the crystal field theory? So if you understand for this complex, titanium H2O whole 6 whole 3 positive complex. The observation is that the complex is violet in color. The color of the complex is violet. Geometry it is having is octahedral complex. You can see 6 ligands are there around the titanium which is binding to it. So geometry will be octahedral. Electronic configuration of here metal ion which is titanium is central metal ion is titanium 3 positive. Titanium in the 3 positive oxidation state. So its configuration will be 3d1. So it is a 3d1 system, meaning it has only one electron in its d orbital, right? Ground state. So for the ground state of complex, the single d electron is located in the T2g level. Okay, because it is a octahedral complex, and in the octahedral complex the lower energy set is T2g set. So this one electron which is having in the Ti3 positive is going to be located in the T2g level, lower energy level. Excited state, if you see, so in the excited state the next higher energy level available for this electron is empty G level, right? Because it is already in the T2g level. For the next higher energy level, the level which is like available is empty EG level having higher energy than T2g level. So you can see this is the ground state representation, where in the T2g we have one electron in the ground state, and this is EG having like no electron, empty, because this is only D1 system in the Ti3 positive. When it is going to the higher or you can say excited state, after losing some amount of energy in the form of light, in the excited state only available energy level is the EG level for this electron to fill into. So this electron will jump from the T2g to the EG level and go into the higher energy level which is EG. So this is the representation for ground state and excited state for the titanium 3 positive complex which is octahedral complex. Now light absorption and electron excitation. So when the light corresponding to the energy of blue-green region of visible spectrum is absorbed by the complex. So light which is corresponding to the energy of blue-green region of visible spectrum, that is absorbed by the complex. And this absorbed energy excites the electron from the T2g level to the EG level. Okay, so when the light of the energy corresponding to blue-green region of visible spectrum, this is going to be absorbed by the complex, and after this absorption of light energy, the electron is excites from the T2g level to the higher energy EG level. Now this transition can be represented as T2G1 EG0 to T2G0 EG1. Okay. The observed color. So what will be the observed color for the complex? So consequence of absorbing blue-green light, the complex will appear violet in color because it is absorbing blue-green region light. So it will show the complementary color to it, which is violet. So complex will appear violet in color. Fundamental principle of color in the crystal field theory. So crystal field theory attributes the color of coordination compounds to DD transition of electrons. Okay. So crystal field theory is going to tell you or is going to explain you the color of the coordination compounds to DD transition of electrons by the helping of DD transition of electrons. If you understand the DD transition, then the crystal field theory is going to come here and going to tell you that what is going to be the color of the coordination compounds. Means that the color which is arising from the electrons will moving between the split d orbitals within the complex. Okay, so because the electrons are moving between the lower and the higher energy level, that means DD transition of electron is happening. That means electron is moving between the split d orbitals within complex. Due to this, the color is arising. Okay, color is appearing in our complex. Absence of ligands and color. Crucial point. So basically, in the absence of ligands, if you have no ligand, then crystal field splitting does not occur, right? What will be the consequence? That substance is going to be colorless, because if ligands will not be there for the bonding with the metal, then there is no splitting of electrons will happen, no excitation of the electron will happen, and no color will be observed in the compound. So substance will be colorless. The examples: heating of TiH2O(6) chloride whole 3 removes water and renders the compound colorless. If you heat this complex, this water will be removed and the compound will remain colorless. Anhydrous copper sulfate is white, or you can say colorless, because there are no ligands to cause the crystal field splitting. And due to the absence of the crystal field splitting, there is no color, which is shown by the anhydrous copper sulfate. Copper sulfate .5H2 is blue in color due to the presence of water molecules which is acting as ligands in it, leading to the crystal field splitting and the DD transition. Okay, and you can also observe alternatively that this complex is having ligand as a water, okay, water as a ligand, water molecule as a ligand, which is going to cause the crystal field splitting and the DD transition, due to which it is blue in color. Influence of ligands on the complex color. Type of ligand significantly influence the color of the complex. So, because different ligands cause different magnitude of crystal field splitting, right? Because we have seen the spectrochemical series. Some are strong field ligand, some are weak field ligand. So, different ligand will cause different magnitude of crystal field splitting in a complex, due to which the color is going to be affect for the complex. The illustrative example is, let's take nickel plus 2 complexes with ethane 1,2 diamine. The starting complex, so when nickel plus 2 chloride is dissolved in the water, the green complex is formed, which is nickel H2O(6) 2 positive. This is green in color. Progressive ligand substitution. So when you add ethane 1,2 diamine, which is a ligand in this complex, a biadentate ligand. So this is a biadentate ligand, ethane 1,2 diamine. This progressively replaces the water ligands which is already present in the complex, and leading to a series of reactions and distinct color changes. As the ligand attached with the central metal ion is going to change, the color represented by the, or color showing by the complex, will also change at each step of the reaction. Okay, so when you take this ethane 1,2 diamine and nickel plus 2 complex, and when you do the reaction of ethane 1,2 diamine, which is a biadentate ligand, that means it is going to have two donor atoms which can make a bond with the central metal ion. So when this biadentate ligand is going to add up into the complex, progressively it is going to replace the water molecules already present as a ligand in a complex one by one, which is going to lead a series of reactions, and at each step the color is going to be changed for the complex which we are getting after the reaction. Okay, so it is going to show distinct color changes. Series of reactions. So the reaction 1 is En ratio nickel. So when the ratio of the ethylene diamine, or you can say ethylene 1,2 diamine, and the nickel, when the ratio of these two are 1:1. So the reaction 1 will follow, which is this complex of nickel having water molecule as ligands, which is green in color, plus you add one ethylene 1,2 diamine into it in the aqueous medium. You will get this complex as nickel H2O(4) ethene, this En, which you will observe the color change here, that is pale blue. So this green complex will convert to the pale blue complex, plus two water molecules will get out from will come out from this complex. The color change here observed is from green to pale blue. Okay, so this is a figure 5.11, which is showing the aqueous solutions of complexes of nickel plus 2 with an increasing number of ethane 1,2 diamine ligands. Okay, so if you have no ethane 1,2 diamine ligand in our complex, then this is going to show green color. If you add one ethane 1,2 diamine into the complex, then it is going to replace the number of water molecules already present in the complex, and the color will also change, which is pale blue for nickel H2O whole 4 En. When you add more ethane 1,2 diamine into this complex, then the complex become nickel H2O whole 2 En whole 2, and the color will be blue. Again, when you add more ethane 1,2 diamine into this complex, the complex will be nickel En whole 3. That means all of the water molecules will get out from this complex, and only the remaining ligands will be 3 molecules of bidentate ligand En, ethane 1,2 diamine. And the final color observed for this complex will be pink, or you can say violet. Okay, so this is the diagram showing the change of color, or this is the diagram showing the aqueous solutions of complexes of the nickel plus 2 with an increasing number of ethane 1,2 diamine ligands, and how the color is changing with that process. So reaction 2 will be when ethane 1,2 diamine ratio nickel is 2:1. So you take this complex which was already made in the 1:1 complex, then you add one ethane 1,2 diamine. The complex form will be nickel H2O whole 2 En whole 2, which is blue or purple in color, plus 2 water molecules will be coming out from the complex. The color change here observed is from pale blue to either blue or purple. Okay, you can see that this pale blue is converting to either blue or a purplish color after the adding of one more ethane 1,2 diamine ligand into it. The reaction 3 involves the ethane 1,2 diamine ratio nickel as 3:1. So in this complex we have already gained. We add one more ethane 1,2 diamine and you get the final complex nickel ethane 1,2 diamine whole thrice, whole 2 positive, which is finally violet in color, and 2 water molecules will coming out from this complex. The color changing from blue or purple to violet. So finally you can see in this test tube we have violet color solution, which is of nickel En whole thrice. So this is the color changing of the process showing in this diagram. When you add different ethane 1,2 diamine one by one with the nickel plus 2 complex, how the color is changing, this is what this diagram is showing. And the final complex forming is nickel En whole thrice having violet color. Key takeaway from the example. So this sequence vividly demonstrates that how changing the ligands even gradually, even one by one, dramatically alters the color of the complex, directly relating to the changes in the crystal field splitting energy, right? So as you are changing the ligands, this is going to affect the color of the complex because it is related to the change in the crystal field splitting energy for a complex, for a central metal ion present in a complex. Let's see the limitations of crystal field theory. 5.5.6 Successes of crystal field theory. The crystal field model is highly successful in explaining several key aspects of coordination compounds, including the formation of coordination compounds, the structure of coordination compounds, the color exhibited by the compounds of coordination complex, and the magnetic properties related to them. So the crystal field model is highly successful in explaining these key features of the coordination compounds. What are the limitations now? There is some limitations for crystal field theory. The first is the assumptions of point charges. So CFT assumes that ligands are point charges, that is purely electrostatic interaction is going to be there between ligand and metal ion. Okay, so it assumes that ligands are point charges. The consequence of this assumption is that based on this, the anionic ligand which carry a negative charge should theoretically exert the greatest crystal field splitting effect, right? Because it is a negative ligand, it is carrying negative charge, it is an ionic ligand. So it should theoretically exert, on the basis of the concept of an ion, it should exert the greatest crystal field splitting effect. Okay, but it is not in all the cases. So that is the consequence of this assumption made by the CFT that all the ligands are point charges. Contradiction with the experimental observation. So it is also contradicting the experimental observations, that in reality anionic ligands are found at the low end of spectrochemical series. If you see the spectrochemical series, at the very lower end, at the very starting end of the spectrochemical increasing series, the iodide ion, bromide ion, SCN negative, Cl negative, S2 negative, F negative, OH negative, C2O4 negative. So every negative, or you can say anionic ligand, is present or are found at the low end of the spectrochemical series, which is a contradictory to its own assumption it made, the CFT. Okay, so this is the experimental observation through which we observe the spectrochemical series, but due to this, the assumption made by the CFT is contradictory to this experimental observation of spectrochemical series, in which anionic ligands are found very at the low end of the spectrochemical series, which should not be the case, because as a theoretical concept, anionic ligand should exert the greatest crystal field splitting energy or splitting effect, right? Means they cause less splitting than many neutral ligands, which directly contradicts the point charge assumption. Okay, so because they are present at the very lower end of the spectrochemical series, the anionic ligand are present at the very lower end of the spectrochemical series. That means they will cause lesser splitting than the neutral ligands, which is directly contradicting the point charge assumption of the crystal field theory. Neglect of covalent character. CFT or crystal field theory does not account for the covalent character of bonding between ligand and central metal atom. The covalent character there is in the bonding between ligand and central metal atom. Crystal field theory doesn't talk about this, doesn't explain this. Treats the bonding as purely ionic or electrostatic, which is a oversimplification. Crystal field theory simply says that the bonding between the ligand and the central metal atom is purely either ionic or electrostatic, which is a oversimplification. It just simplifies the bonding into only one term, that it is only ionic or purely ionic or electrostatic. It doesn't account for the covalent character between the ligand and the central atom, if can be there or so. It doesn't explain anything about that. More advanced theories. So, weaknesses of crystal field theory are addressed and explained by more advanced theories. Okay, whatever the limitation or weakness of crystal field theory is, they are addressed by the more advanced theory later, such as ligand field theory, molecular orbital theory, LFT and MOT. These are the theories which explains the weakness or the limitations of the crystal field theory in detail. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.